Hello and welcome to a new very interesting video. This video is about this little device here. It's a multi-function tester. It is there for testing components, and if you follow my channel you might know that I repair electronic equipment like oscilloscope, tape recorders, radios, amplifiers and a lot of cool stuff. Among other things, of course, I also build circuits and so on. And currently I repair a Tektronix 549 oscilloscope, and unfortunately the tube which generates the reference voltage for the power supply was broken, so it was open, and therefore the power supply voltage, all voltages in the oscilloscope went quite high. And this oscilloscope is a hybrid of transistors and tubes, and so I needed something to check the transistors, because I want to make sure that no transistors are damaged. I want to find out which transistors are damaged. And since the transistors in this oscilloscope are socketed like tubes, you can easily remove them and test them. And so I thought, I went to the electronics store. I'm in Austria, so I went to the Conrad electronics store. And I asked them if they had a transistor tester. Yeah, of course, a multimeter can also test diodes, but I asked them for a real transistor tester where I can plug the transistors in and test them. And they gave me this. And the amazing thing is, it was quite cheap. I think it was 23 euros or so. And this thing is so much more than just a transistor tester, I can tell you. So it's really worth the 24 to 23 euros. So I'm not in conjunction somewhere with them, but this is really a really good piece of test equipment actually. From the build quality, it's not the highest standard, it's pretty cheap constructed actually, but what it does is just amazing, right? So it still has its protective cover on here, as you can see. So you could peel that off or wait until it peels off itself. I will let it on here. And yeah, now let me show you what it does. So first of all, it's not just a transistor tester, it's actually a multi-function tester, which means you can test transistors, you can test diodes, you can test capacitors, you can test inductors, you can test Zener diodes, you can test field effect transistors and so on. So you can test a lot of stuff with this thing. And yeah, now this is gonna be a review of it. So first let me show you what's in the box actually if you purchased it. So you get the device with this protective cover, of course, so we could peel that off. Shall we peel it off? Let's do it together. Let's do it. Okay, so oh yeah, so okay, now the display, you can see the display, and it comes in this USB bag here, and included are these 3 test leads here with these clips at the end. Again, the build quality is not really high, but it's just 25 or 23 euros or so. So actually, if you Google it, you find it between 20 and 30 euros, I would say, currently, at the time this video is uploaded. And also this short USB cable is included. So it has a battery inside, and you charge it via this USB cable. You charge it via USB. You can use your mobile phone charger, or you can use your computer, and while it is being charged you can also operate it. So you have this plug down here, just plug it in like this, and then connect it to, in my case, to my computer. So here this is my computer, and I connect it. So, and now it's charging, and you can see this red LED indicates that it is charging. Okay, and I can disconnect it. Of course, this is a standard USB connector, so you can also buy a longer cable if you need one. Alright, then it comes with this thing here, and with one capacitor and with one LED. So this already reveals that this thing can do more than just test transistors, because this is not a transistor, and this is maybe a bit nearer a transistor, but it's still not a transistor. Okay, so yeah, let's see what we can do with it. And to test something, yeah, let's start with a transistor. So this is a transistor. It's a well, let's take this transistor here. It's a BC547PB. So this is an NPN transistor. The other one is a PNP transistor, it's BC557B. So let's test the NPN transistor. So you just plug it into here, then close it with this lever here. So put it in here and close it. Now the transistor is in it. Let me zoom in a bit more. So there we go. And I press the start button. Now it says testing. And here we have the transistor. And the amazing thing about this is that you don't have to care about the pin out of your transistor. You just plug it into here. So in the first row we have here pin 1, 2, 3. It's numbered. I hope you can read it. It's 1, 2, 3. And you just plug it into here, and it will automatically detect what the device is. So if it's a transistor, if it's a diode, a capacitor, and so on. And then it will also show you the pinout. So let me do it again. I press test. So now it's testing. It also shows the battery voltage, which the device currently has. And here you can see, now pin 1 is the collector of the transistor. Pin 2 is the base of the transistor, and pin 3 is the emitter of the transistor, which is right. If you look up the datasheet of the BC457B, then if you view it front on, so the flat side facing towards you, then you can see that we have a collector, base, emitter, and this is exactly what this is showing. So it shows me the transistor. It's a BJT, bipolar junction transistor. It's NPN, and it also shows me the current gain, HFE. It is now 391. This is the current gain of this transistor here. Then it shows me the base emitter voltage, so the diode drop of the base emitter diode, which is 685 millivolts, which is also fine. And it shows me the collector current at which this was tested, I suppose. Okay, so now let me show you that it doesn't matter how you plug it in. So if I reverse the transistor like this, and if I test it again, as you can see, it's still the same transistor, but now the pins have changed. So pin 1 is now the emitter, pin 3 is the collector, and pin 2 is still the base, and this is of course right. So we have the emitter right here. So if the flat side is facing towards you, this is the emitter, so it's automatically detecting the transistor, which is just great. Okay, so let me remove that. And before I continue showing you what else it can do, in the manual they say you should test the device before using it, and it has a self-test function built in. So to start the self-test of this device, you have this thing here, and you plug it in like that. You can see like that. So it starts with the second pin and so on. And now if I start it now, it's in the self-test mode. So you can see now it's a self-test mode, and now it's testing itself, and we just have to wait a bit. And now please isolate probe. So now we have to remove this thing here, and now it continues testing. A little bit. And now it has completed the self-test without any errors. So yeah. Okay, so let's continue exploring the thing. So we have already tested the BC547B. So now let's here test the BC557. So this is a PNP transistor. So this means that the diodes basically of the transistor facing inwards. So let me test that. And you can see it automatically detects it's a PNP transistor. You can also see that the symbol is right. And we have a current gain, we have a base emitter voltage and a collector current. Great. Okay. So it does this very well. Okay, so now let's test some capacitors. Here I have an electrolytic capacitor. It has 100 microfarads and 35 volts. It is polarized because in electrolytics it has a minus and a plus. And now I plug it in between, let's say, pin 2 and 3, because it doesn't matter. I can plug it in wherever I want and it should detect automatically where it is connected. So let's see what it does. It's testing. And there we go, it has detected a capacitor between pin number 2 and pin number 3. Pin number 1 is open and this is exactly what we have. Amazing. Let's see, the capacitance is 98.85 microfarads, which is fine. And then there are some other parameters which it indicates. It indicates the ESR of the capacitor, which is in this case 0.06 ohms. And the V loss of this capacitor, which is 0.7%. So let me very quickly explain what this actually is, because these are some very important additional indicators if the capacitor is working fine, because sometimes you can have a right reading on the value of the capacitor, on the capacitance value of the capacitor, but the ESR might be too high, and now I will show you what it is. So here I have prepared this this sheet for you, and ESR is basically a parasitic series resistance which is inside the capacitor in series to the capacitor. So it's inside, you cannot actually reach it, you cannot remove it because it's in the capacitor. ESR stands for equivalent series resistance, and basically if you operate the capacitor at high frequencies, then it will act as a short, because a capacitor at high frequencies is like a short, and a capacitor at DC will just charge and will be like an open circuit. So ESR is something that is measured with frequency, not with DC, which is measured with alternating current. And basically, if this ESR is too high, then it might block some of your signals which should pass through the capacitors. So for example, if it decouples in two audio amplifier stages and you have a very high ESR, then it might not, the signal might not go through and the amplifier is not working. So therefore this ESR is very important to check if it is low. In this case 0.06 ohms is fine, and the ESR is also dependent on the capacitance and on the frequency at which you test it. And you can find tables which show in which you can find different capacitance values and the ESR that the capacitor which this value should have, and then you can compare your capacitor and see if it is fine. Another thing you can always do is, if you have a capacitor which you know that is good, for example, you have a good 100 microfarad capacitor and you have a capacitor which is maybe broken, then you can compare it with this device. You can compare the ESR and see if the capacitor is fine or not. I have to mention something else. There is not only this ESR thing. In a capacitor there's something else that can happen, and this is leakage. Leakage means actually this is a DC thing. So if, as I said before, if you charge the capacitor, it acts like an open circuit, like a resistor with an extreme high resistance. So actually, but leakage is if it is completely charged and if it is like an open circuit, then it could be that there is a parasitic parallel resistance in the capacitor. And this parasitic parallel resistance, there's current that can flow through this parasitic parallel resistance. So there's current that can leak through the capacitor even if it is completely charged. So you have a parasitic parallel resistance which passes current even if the capacitor is completely charged with DC. And this can be problematic because, for example, again in an amplifier, a capacitor is there to block DC from different stages, because one stage could have a DC offset and the other stage could have a DC offset, and the capacitor is there to block the DC offsets from one stage to the other stage. And if it leaks, then it might not be able to block this DC offset completely. This could be actually quite dangerous, for example in tube amplifiers. If the capacitor in a tube amplifier which blocks the DC from the anode to the grid of the next tube stage, then it could happen then that you drive the grid of the next tube stage extremely high, and the grid will draw current and the tube will draw excessive current, and this could cause red plating, which actually destroys the tube. So parallel parasitic resistance or capacitor leakage is also important. This device does not measure this leakage resistance. It measures ESR, which is already a pretty good indication, but it doesn't measure leakage. Actually, there's a hint. If a capacitor has leakage, and if you measure it with a multimeter, with a device which can measure capacitance, then most of the time the capacitor actually reads high. It reads higher than it should be, because the device measures how long it takes to charge the capacitor, and if you have a low leakage resistance, then it takes longer to charge it, and then it measures high. So this could be the case if you repair something old and you find, okay, I have some capacitors which are rated for 10 microfarads and actually they have 15, then this is not an overachiever. It could just be that they are leaky and you should replace them. Alright. But this device has shown us something else. If I turn it on again, it has also shown us something which they call V loss, and this is 0.7%, and this is also known as DF, dissipation factor, and the dissipation factor is the ESR divided by the impedance of the capacitor, divided by the XC. So this is the impedance of the capacitor, and it is also known as Q. Maybe you know this because Q is 1 over the dissipation factor. So actually you want to have a capacitor with a high Q or a low DF, low dissipation factor. In this device, the dissipation factor is measured in percent, so you would have to multiply this by 100, then you get the percent of your dissipation factor. And yeah, but this yeah, that's it. Okay, so now let's check how accurate this device actually is, and for doing that I will use my LCR meter here. So this is a more expensive device to test inductors, capacitors and resistors, but it is not as multi-purpose as this, so it's just for this task and very specialized, and this is a multi-purpose device, and for me it's a bit more handy for repairs to use this one. This is more for if I build a circuit, for example, if I create an inductor, if I wind an inductor and if I want to check how high its inductance is, then I can use this device. So it's quite handy for such things where I also need precision, but for quick tests this thing is just amazing, as I said before. So let's see how accurate it actually is. So I will test this capacitor now with my LCR meter and see what we get. So it has automatically detected this is a capacitor, and it shows me 94.22 microfarad. And let me go into the mode where I can measure. This is the Q of the capacitor. I want to measure the ESR. So the ESR of the capacitor is 0.10 ohms. And as I said before, the ESR is frequency dependent. So we are measuring this now at 1 kilohertz, and I could also change the frequency at which it is measuring the ESR. But now let's stuck at 1 kilohertz, and now I go into the hold mode, so it freezes the value so that we have it here still to compare it. And let's compare it because it's still on the display. So the capacitance reading is at least accurate enough because it reads 98.5, and the ESR meter reads 94.12, so this is accurate enough. And also the ESR is accurate enough for me because it reads 0.07 ohms and this reads 0.1 ohms, so this is fine. And actually I don't know at which frequency it is measuring the ESR, so it could be even more accurate, but this is absolutely fine. This is perfect for what I needed, and I'm pretty sure that it is also perfect for your troubleshooting if you use it to test capacitors. So while we are at it, let's test another capacitor. Okay, so now let's check another capacitor. Here I have this ceramic capacitor. It has 47 picofarad, which is pretty low for this device, I think, because let's see if it actually does it. So first test it on the LCR meter. So we have 47.6 picofarad, so it's a pretty accurate capacitor. And the dissipation factor is quite low. It's 0.001, so not 0. So actually it's extremely low. So I think this thing cannot measure it. Maybe it will be just 0 or just not being displayed. So let's put it in here and compare it. Now I've plugged it in between pin number 1 and 3, and we have a capacitor from pin number 1 and 3 with 47 picofarad. So this is perfectly fine, and we don't see any ESR dissipation factor because it is extremely low and therefore not measurable. But not a problem, because if the capacitor is fine, it should be low, and if it's not displayed, then yeah, it's fine. Okay, so now let's check one last capacitor before we move on. Let's take this one here and check it with the ESR meter, with the LCR meter. And let me put this on hold. So we have 455 nanofarads and we have an ESR of 0.02 ohms. And the great thing about this here, you can also plug in bigger capacitors because the pin 2 and 3 and 1, they are repeated on here. So these are internally connected. And let's start the test. And what do we have? We have 0.0 ohms ESR, and this thing reads 0.02, so this is fine. It's because it's that low. And we have 459 nanofarads, 450 nanofarads, so perfectly accurate. Okay, so that's for the capacitors. And we can also check some inductors. So for example, this one here. So let me plug in the inductor here, like so, and test it. And we have an inductor. We have 0.11 millihenry and no series resistance between pin number 1 and 2, so 0.11 millihenry. So let's see what this gives us here. And we have 90.2 microhenry. 90.2 microhenry. This is 111 microhenry. It's good enough. It's good enough. So let's see what this inductor gives us. 439 microhenry. 438 microhenry. Let's see what we get here. And we have 440 microhenry, so it does inductors quite well, as it should. Okay, so let's put this aside. Okay, great. So now let's test some diodes. So here I have a diode. It's a 1N4007, I think. Yeah, it's 1N4007. And if I plug in the diode like this between pin number 1 and 2, let's see what we get. And we have a diode. We have a forward voltage of 0.661 volts, and this is the capacitance of the diode, which is especially important if you use it for switching applications or RF applications. So let me check another diode. I think there's a 1N4148 diode. It's now between pin number 1 and 3. And there you go, we have again the voltage, 0.691 volts, we have the capacitance, and we have ER. This is the reverse current of the diode, and in this case it's 2 nanoamps, so this thing goes quite low, so it can measure the reverse current of the diode. Great! This is amazing. This is just amazing. So let's test a special diode. This diode here is a Zener diode, okay? And let's plug it into here. Now it's between 1 and 2. And let's see what this does. Here we have the Zener diode, we have a forward voltage of 0.779 volts, and we have a capacitance and a quite high reverse current, 1.7 microamps. And why is that? Because a Zener diode is actually made to act as a voltage reference of some sort, so it has a reverse breakdown voltage, a defined reverse breakdown voltage, for example 12 volts, 20 something volts or so. And with this you can use it as a voltage reference, so it breaks down at a specific voltage. But this thing is not displaying it, because if it connects 20 or 30 volts across this terminals, it could potentially damage some components. So to prevent this, there are some special terminals down here, these 3, and these are made only for Zener diodes. So I connect the Zener diode in the right direction from anode to cathode, which is like this here. Now come on, like this. I've connected the Zener diode and I run the test again, and now it's in Zener diode, and you can see now it's testing the Zener voltage. In this case it's 5.93 volts, and it also displays that it is a Zener diode, so it has also a special Zener diode tester built in, and I think it goes up to 30 volts according to the data sheet of this thing. So what else have we got here? We have a MOSFET, and amazingly, if I connect this MOSFET to that, it will also test the MOSFET. You can see it has completely detected everything what it is. So we have a MOSFET. This is a P channel enhancement MOSFET. Here the gate is now pin number 1, drain is 2 and source is 3, which of course it is. Here it has detected the voltage across the diode in the MOSFET. Then it has the threshold voltage of the MOSFET, which is 3.54 volts now, which is quite handy to match MOSFET. Actually, if you want to match some MOSFETs for whatever reason, you can use this. Extremely useful. You have the gate charge or the gate capacitance CG of the MOSFET and the RDS, which is the resistance between drain and source when it is on. These two parameters are very important for switching applications. You want to have a low gate capacitance which allows it to turn it on quickly, because it doesn't have to charge so much, and you want to have a low RDS on because you want less dissipation on the MOSFET if it is on, and if the resistance is low, then you have a low power dissipation on it. So amazing. It is. I'm just amazed what this thing can measure. So let's measure another MOSFET. This is another MOSFET, and we have an N MOSFET, and of course it is an N MOSFET. N enhancement MOSFET, the pins are right, amazing. So let me see if I can get the JFET. So what is this here? J176. Let's test this J176 JFET here and see what we get. And we get a PG JFET, okay? With what do we have? A gate voltage of 1.05 volts, and at this gate voltage we have 1.5 milliamps. So now you can compare this with the data sheet or with the characteristics curve of the MOSFET of the JFET, and then you can see if it is working perfectly fine. If I have an N JFET, if you know a bit about vacuum tubes, actually a vacuum tube, a triode or pentode behaves quite similar to an N JFET. So this is P, this is the reverse of it. So I suppose that in the N JFET you would have a negative gate voltage, of course. So let me see if I can get an N JFET. So what have we here? We have this very famous BF245C. This is an RF N JFET, and let me test it. And of course N JFET And there we have it. At a grid voltage, at a gate voltage of 0.475 millivolts, we have a drain current of 680 microamps. Amazing. And I'm pretty sure that this is what it is. Okay, so now finally let me show you a bit what happens actually if we connect components that are not working to this thing. As I mentioned at the beginning, and currently I'm repairing a Tektronix 549 oscilloscope, and this is one component which is not working. It's a capacitor, and let's see what we get from this. This cannot be plugged in here, but we have these wires which you can connect to the device. Now I connected between pin number 1 and 3, so this is a bit a clunky solution because you have to plug it in here and close this, but it will do. And now I connect it. Oops. Now I connect it, and let's see what we get. And there we go. Actually we have just a resistance of 13.3 kilo ohms. So this is heavily leaky, and it is so leaky that the thing just detects it as a resistor. So this is a broken capacitor, as broken as it can be. And yeah, this was also in the power supply of the Tektronix, and therefore the voltage was completely off. I think this was for stabilization, so that it does not oscillate. And yeah, it did not oscillate, but it also did not work, so I had to replace it. What else have we got? We have, of course, we have some tubes here, but I cannot test tubes with it because it has no filament heating, and it has the voltage is too low. So here I have another capacitor, and this is 0.5 microfarads, 400 volts, and this is also not working. And let's see what we get from this. And let's push the button, and let's see. And we have an interesting result here, a very interesting result. It shows me a low ESI. It has 0.58 ohms, so this would be fine. But the problem here is we have 910 nanofarad, which is almost the double of what it should have. This is almost 1 microfarad, and it should have 0.5 microfarad. And this is exactly the point I mentioned before. This capacitor is leaky. It has a low parallel resistance, and the device needs more time to charge it, and therefore it shows a higher capacitance that it actually should have. So it shows no leakage, unfortunately, but this gives me a clue that this thing is actually leaking. Okay. Yeah, so this is the failure mode of this capacitor. By the way, let's see what this capacitor, which we had before, which with the 400 with the low parallel resistance, which was highly leaky, what this gives us on a normal multimeter. So if I use this normal multimeter, a multimeter also has a capacitance test mode, which is this position here, and let's see what we get here when I connect it. Okay, so this is broken in such a way that it is broken. So here I have a very interesting failure for you. This is a broken transistor, and it was in a Sony Trinitron KV1300E, a color television of the early 70s. And this was in the, actually this television is hot chassis and has a switch mode step down converter in it, which converts the 220 volts down to the system voltage of 110 volts internally. And this was the switching, the chopper transistor. And the interesting thing is, if you test this transistor with a multimeter, with the diode check, it almost checks fine. But if you test it with this device, you will find out that it is not fine, and I will show you. basically the way this transistor is NPN, and the way it is connected is that this is the base, then the housing of the transistor is the collector, and this pin here is the emitter. Base, collector, emitter. And now first let me check this with a multimeter to show you what the diode test does. So here I have my multimeter. I put it into the diode position. Actually, put it like this. So okay, now it's in the diode position, and I will turn it on. So of course now it's open. Now it's 0. And if I connect the base here and the emitter here, then we have 0.46 volts. So it's a bit low, because diode, you know, it should be 0.5, 0.6 or something. So it's a bit low, but it's still somewhat the diode. And if I connect it to the emitter, base to emitter, I still have 0.46. So for example, this one here is a working transistor. It's not the same type than this. So this is not the same type than this, but it has the same pin out and it is working. So they're connected to the base and to the emitter, so we have 0.55 volts and 0.55 volts, okay? So basically, if you look, so you could think it is working. Actually, there is an indeed that it is not working, and this is because if you check it from collector to emitter, it's just short. So can see it's dead, completely short. And if you check the good one from the collector to the emitter, it's good. So basically you can check it with the multimeter, but let's see what our device, our component tester gives us. So let's see if we get more or a better reading. So here we have the tester, and now I need 3 leads. Of course I cannot plug it into here because so there we go. And yeah, let's first check the good one. So this is the good one. So we have base, collector, and emitter. There we go. And let's see. Of course we have a good transistor, base, collector, emitter, current gain of 82, base emitter voltage of 0.5 volts, and yes, everything fine. And now let's check the broken one, and let's see. So actually we have a short between collector and emitter, but the diodes are still somewhat okay. So let's see what we see on this thing, if it reflects the same, if it has the same result. And of course this is quite interesting. We see the diodes from base to collector and from base to emitter, so these are fine. I don't see the short from collector to emitter because it is shorted on the multimeter, but it is 2 diodes. So actually quite interesting reading, right? Quite interesting that it works that way and it can display the result that way. Yeah, while we're at it, let's see what it does with a potentiometer. So let's see. Potentiometer, as you know, has the sliding contact in the middle, so I connect it to the pin 2, and here we have the outer contacts. So between the outer contacts we have the full resistance of the potentiometer, and of course we have the resistance from here to here depending on the position where this is. Okay, so let's check it. And we have 2 resistors, one with 18K and the other with 9K. And if I adjust it, then we still have 2 resistors, one with 23K and one with 300 ohms. So it automatically detects the network that the potentiometer is creating, so to speak, and it can also measure this. Isn't that amazing? I really enjoyed that it does such cool things. Actually, yeah. So let's remove this again, and basically there's so much more to test with it, but it can also test infrared television remote controls, I think. Yeah, so let's finally, since there was an LED included, let's finally test the LED and see what it does with the LED, because if it's included we should test it, and it lights up. And there we have the LED, a forward voltage about 2 volts and 4 picofarads. And I know that you're curious seeing what signals are actually on these connectors here, so what it actually does. So I will hook up an oscilloscope to the thing and see how it measures and what it actually does measuring something. So connect the black one to ground here, and connect the red, or no, let's connect the green one to signal. And now let's move to the oscilloscope. Okay, so now the oscilloscope is on, and for this it's maybe better in digital mode because I can single shot it, and I can adjust this here to ground. And now as you can see it's a bit jumpy because we're getting 50 Hertz hum, because this thing is now completely open. When it is off it seems to be completely open. So now let me press the button and see what's happened. So now I will push the button on the device. Okay, and it's doing something, and now it has detected my oscilloscope as an 11 megohm resistor, which it actually is. Let me see if I can single shot this whole process. I go into single sweep, and yeah, let's put the level to 2 volts or so. So, and now let's push the button. Okay, this is what it is doing. Let me do that again. It's a bit up, down, down, up, down. Yeah, this is what it is doing. I won't analyze this now, not more in detail right now, because I don't want to. But if you're interested, this is what it's doing. It's high impedance, then it's doing this dangly dingly thing, and then it goes back into high impedance again. Let's see what happens if we connect the capacitor in parallel to it. Let's see how it figures out the capacitance. And now we have a capacitor in parallel to the oscilloscope. So the oscilloscope is still on here, the capacitor is in parallel. Let's see what happened now. And of course I have to put it back into single shot mode. And now it is, and let's start. Okay, and this is what I've expected. Actually, it charges the capacitor and it measures the time, how long it takes to charge it. So let me do another single shot. There we go. There you can see it charges the capacitor. This is the charging curve of a capacitor. So since it has this function, it's not a constant current, because if you would charge it with a constant current, then you would have a ramp. Since you have this exponential function, it is charged with a series resistor, and so it just measures the time, how long it takes to reach a certain voltage level, and from this it computes the capacitance of the capacitor. So again, what I said before, if you have a leakage capacitor with a parallel resistance, which a low parallel resistance with a high leakage, it takes longer for the capacitor to charge, so it takes longer for it to reach a certain level, and this in turn means that it reads a higher capacitance that it should actually read, and therefore this capacitor, which is leaky, reads double of the capacitance because it just takes longer for it to charge. And yeah, so you would need a specific capacitance leakage meter for this. But this is how it is doing its thing, right? Okay, great. So this concludes the review of this multifunction tester, which tests just so much, and I really enjoy this device. The build quality is not that high, but for the price it's absolutely fine. And of course it's not extremely accurate, but it's accurate enough for quick checks, and it's perfectly suited for troubleshooting. So I really enjoy it, and I would highly recommend you to buy such a thing if you repair electronic equipment, or if you maybe you can also use it to test components if you build something and so on. So, but if you repair it, it's just a must-have. You have to buy it. That's the point on it, because it's so cheap. If it would cost 100 euros, okay, then it's something else. But if it's between 20 and 30, it's just a must-have. Yeah. So this concludes the review video of this little device here. And I can say thanks for watching. I hope you have enjoyed this video, and see you in the next one. Bye!